This is part 13 of lecture 11 of ELEC5300. In this final part, I'm going to describe the relationship between the deterministic least squares solution and the Kalman filter, because intuitively you can kind of think that they're kind of trying to solve a similar problem, right, which is that of estimating some kind of unknown quantity. Let's go back and look and review the Kalman filter. So you remember that the Kalman filter has a vector model of the measurements and the underlying state that wants to be estimated. Now in this case here, what we're going to do is we're going to assume that we're trying to estimate a constant, right? So the constant here just has this vector formulation where at every point in time the previous value is the same as the next value, or the current value, or the next value is the same as the current value, right? And then the observation is just some linear transformation of x plus some measurement noise. We're going to assume that we have no prior knowledge about what the x is, right? So one reasonable assumption in that case would be that, well, our prior estimate of x is 0, but that has infinite variance, right? So really, actually, it doesn't really matter if I have infinite variance. It doesn't really matter what this is. And we'll see that that actually drops out in the equations. So when we use the alternative Kalman filter, right, because we have this kind of problem where the variance is infinity, the alternative Kalman filter gives us a way to solve that, right? So if we want to find out the variance after the update, right, that's P0, right, from the variance before the update, which was infinity, I can do that in terms of inverses, right? So this is kind of like dealing with the precision, right? Originally I had infinite variance, or 1 over the variance then would be 0 precision, right? And then after I take into account a new measurement, I should get improved precision, or a larger precision, and this quantity here is the increase in the precision, which when increasing from 0 is just given by this. So the new precision is given by this, and then once I have that, then I can compute the Kalman gain according to this equation here, and then substituting in the form for PO inside here, then I can get this equation here, right? And then I can substitute that into the Kalman update equation, right? So that's just the new update is just the old value plus the Kalman gain times the observation error, right? And then what I can do is I say, well, this is just K0 times, this is K0 times Z0, which is this thing here, right? And then what I'm left over with is just, so I have this K0, Z0 from here, and then I get a plus X 0 minus hat, right, minus K0 H0 X 0 minus hat, right? But this thing here is just the identity matrix, right? If I take, this is K0 here, and if I just multiply here by H0, right, then you can see I'm going to get exactly the same thing here and here, and that inverse is going to give me the identity matrix, right? So then I just get X0 minus X0. So this is what I said. If I have infinite variance here, then it really shouldn't matter what my initial mean is. And so you can see the X0 minus dropping out from the equation. I get this, and this is exactly the same solution as in the least squares case. So finally, I'd just like to give you an example of this. Suppose that we want to estimate the gravitational constant. So we went to a new world, for example, and we don't know what the gravitational constant is there. Right? So one way you can try to figure out what the gravitational constant is, you just have a known mass. And you measure, you let it fall from some location, and you measure its location at subsequent intervals, t1, t2, and so on. Right? So let's say you start your initial position and velocity at 0, right? And then you just let it fall, right? And so the thing is going to fall down, and so the measurement sequence is going to be some kind of quadratic function of t, right, as the thing accelerates, right? And so the measurement sequence is just, well, the gravitational constant, which is x, right? And then this is the gravitational constant time 1, time 2, time 3, but here I'm going to assume that it's all constant here. And then this is the noise added to each component, right? So if I look at this and formulate this in the Kalman filter framework, what I have is, well, the state transition matrix is just 1, right? So this is the state transition matrix. There's no noise driving this, right? So Q is 0. The RK here is just a sequence of white noise. Everything is here. And then the H is just a time-varying readout matrix, right? Because I'm taking the gravitational constant and I'm multiplying it by something, but the thing that I multiply increases with t, right? That's corresponding to the mass falling and accelerating, leading to larger and larger displacements from the starting point. So the Kalman filter can actually deal with this, right? Because the h sub k can vary with k. So this is the way we can start it. We can assume no prior knowledge of g, right? What we do then is we say, okay, I have this 0 starting estimate, but it has infinite variance. I update to get a new starting covariance after the update. That gives me then a new uncertainty, right, which is given by this. Then I can substitute that into the Kalman filter gain. Right? When I substitute that into the Kalman filter gain with all of the parameters that I had before, I get 2 divided by T1 squared. And so now when I do that, I can get this equation right here. And there's a slight mistake here. I should have a z1 minus h. So there should be an h1, okay, inside here, right? So when I have the h1 here, remember h1 is given by this. This is going to cancel with this, so I'm just going to get this minus x1, and so then I'm just going to be left with this, right? So this is kind of the first thing you'd expect to do because you have the infinite uncertainty about x, your initial estimate, so you're just going to take whatever data you have and just completely trust that as being a noise-free measurement, and then if that was a noise-free measurement, then you can see here, I would say, well, this is 0, and in order to get x, I would just divide by this, right, which is exactly what happens here. Now what you do is you have an uncertainty associated with that, which you can then use to incorporate new evidence from the next time step to get a better estimation of g, and that will in fact be a least squares estimation of g, right, but it's a recursive formulation of that. So I don't have to look at all the measurements at once. I can look at them one at a time and get an improving estimate of g.